Hello, this is section 1.7 for Calc survey, and today we're going to be continuing our discussion with exponential functions and focusing in on growth and decay. So you'll notice the formulas in this section are all the same. P equals P initial e to the kt, where that K is that continuous growth rate. And watch for that word continuous. Then we'll also do a couple doubling time and half-life problems that I know you do in science, and you've had a little exposure to that in pre-calc and algebra 2. So the most important thing is later on in this section, there are two big topics that you'll definitely want to listen to, and they're very common problems. So make sure the first part of this video is going to be a review, but the second half is what you really want to pay attention, okay? So, and I'm not going to go through all of these examples, but the key thing is if ever I skip a step and you're not able to get the answer that I've gotten, since I'm just briefly going through these notes, email me if you get really stuck and I can show you more steps. I can email you back a picture of my detailed steps. Okay. So this first problem, population of the world was about 4 billion on January 1st, 1975. Assuming that an exponential growth model with k equaling this decimal is appropriate, when will the world population reach 10 billion? Okay, now notice they didn't specify what formula to use, but they did say k equals this decimal. We are talking about this function, but usually with half-life problems, doubling time, exponential growth, oftentimes you'll use the e to the kt formula, but I'll show you later on in the video where you will need to be very careful if they give you a rate and they'll label the rate on what it is. So if it's a compounded rate of some kind, or if it's a continuous growth rate, well, you'll want to pay attention to that. So the most important thing I have students do is make sure you write the model. P equals 4 being your initial. And notice I just wrote 4, not all the zeros. Just keep in mind that this is in terms of billions. E, and then there's my k value times t. So now that we have our model, then we're going to set this equal to 10 so that we can solve. And here's where I skipped all those algebraic steps. So divide by 4, natural log both sides, divide by the decimal, and there's your answer. And you have a graphing calculator. You can do all of those steps in your calculator, and you don't want to round until the very end, so it's good to keep that data in your calculator. Okay, so, and also note that sometimes it'll ask for the year, when will the world population reach 10 billion? If you answer with 46.3 years, that's probably not the best answer, so adding in that to 1975, that would be in the year 2021. Now, also note, be careful with decimals. If this was 0.9, it would still be during 2021. You don't want to round up with years. It's just going to happen during that year. Okay. We'll talk through one more. So, human hair from a grave in Africa proved to have 74% of the carbon-14 in living tissue. Given that carbon-14 has a half-life of 5,570 years, determine how many years ago the body died. All right, so I know you do these in science, but the first thing is you need to get the rate. So that's where the half-life is going to come into play. So P initial all over 2 equals P initial e to the k times your half-life time, 5,570. So we're trying to figure out how long it takes, or that k value, we know how long. What is this rate to cut our initial value in half? So P initials cancel, and I know this is generally where you start with in science class, but it's good to see why. Natural log both sides, divide, and that's how I'm getting the k. Always round your k to 4, 5, or 6 decimal places. Okay, just so you're getting a better answer. So now we have our model up here, and it says we have 74% remaining. So 0.74 times P initial equals P initial e to this kt. P initials cancel, natural log both sides, divide by that decimal, and there's your t, your years old. Okay. And then I believe the next example is pretty straightforward as well. Getting your model, getting the rate, and going from there. Okay, so in this case, you're given the initial and another ordered pair. So you plug that ordered pair in to solve for the K value. So 3 slightly different types of examples, but you need to practice these problems, right? Now, the next type of problems that you might remember, these are your financial problems. So interest is compounded annually. We've already been working with this formula. Remember, this is the A equals 1 plus R. And then compounded n times per year. So n being, if it was semi-annually, it'd be 2, quarterly 4, monthly 12. And then lastly, here's your continuously, P initial e to the RT. We've been calling this K, but same thing. But do note that these R's are not the same. Okay, so here are 3 different financial problems, and they're all pretty straightforward. You've deposited $35,000. How long will it take for this to grow to 50,000? And they gave you the percentage, and notice they said compounded annually, so that's this formula. On the next one, compounded continuously, so we're using another formula. So they're specifying the rate, so you have to use the correct formula. But from there, it's just an algebra problem. So for this one, divide over the 35,000, natural log both sides, pull the t down, divide that. This would be these 2 are really good problems. Well, all 3 of these. Go off to the side, try working them by yourself, and see if you can get the same answer that I'm getting. And if you're not, you need to email me and let me know if where you're having problems and if you need to see more steps. I will happily do that for you. All right, so hopefully those first 2 chunks of the notes review. Now here's where we're getting into the new stuff. So now we're going to use these formulas to help us make some financial decisions. So comparing the future value or comparing present value to determine which option is better. So just a quick example, if you won the lottery and they offer you $5 million today, or you get $1,000 every week for the rest of your life, what would you pick? I'd pick the 5 million. Just, you could die in 2 weeks, who knows, not to be morbid, but that would be my decision. But anyways, that's kind of what we're going to do. So now notice, here's the formulas we're going to use. Compounded annually. So this is normal. B is our future value. B equals P times 1 plus R to the T. That's normal formula. Now what we're doing is we're going to solve this for P. We're going to solve it for present value. So divide over that binomial to the T. And then just simply move it up to the numerator. And of course, to do that, you have to change the exponent to a negative. And there's our new formula. But these are exactly the same, just solved for future, and this one's solved for present. Then continuously, same idea. B equals P to the RT. Divide over the e to the RT and move it up. And it's the same formula, just solved for different values. All right, so let's use this. So present and future. Let me try to get this so you can see it. So a person wins the lottery and is offered the following 2 options for payment. 1, 2 million lump sum payment, or 4 equal payments of $525,000 at the beginning of each year starting now. All right, so here we go. You want to compare present and present, future and future. And I'll explain here in a second. So let's find the present value. So if you're given $2 million today, that's what it's presently worth, $2 million. So that's option 1. Now we want to figure out the present value for option 2. So the first payment you get is that's what it's worth today. But the second payment, what is that worth today? If I was to put it in the bank account and let it sit there and earn interest, what would I be putting in the bank account today for it to turn into $525,000 a year from now? So that's where we're using this formula to work backwards to figure out how much money that is today. And that's what this will give us. And then the one we get 2 years from now, that's this amount, and the one we get 3 years from now. Put these all in your calculator, add them all together, and this is what you get. So which is better? Which is higher? This 2 million versus this 1 0.9 million, we're definitely going with option 1. Good to know. Now let's use future value. I'm going to scroll up here. All right, so future value of $2 million. Now here's where it gets a little tricky. You get a payment today and you get another payment a year from now. That's technically 2 payments in 1 year. So that's why you'll notice it's 2 million e to the 0.04 times 3, because we're getting the last payment 3 years from now. And that's what we're trying to time it so we can compare that the day we get this last payment of 525,000. So 2 million e to the 0.04 times 3. And there it is, that's the future value. Then the future value of what you get today, you'll get to invest for 3 years. What you get at the end of the year, you get to invest for 2, the third one, and then there's the last one. And that's the day that we're comparing the 2 values. And there it is. And you can see 2.25, and here you get 2.23. So of course, option 1 is better. And you'll always get the same answer, but you cannot compare the present value of option 1 with the future value of option 2. That does not work. You need to stay consistent and compare future value for both options or present value for both options. I'll have students who will do future for option 1 and then they'll do present for option 2 and try to compare those, and that doesn't work. Okay, but you'll always get the same answer regardless of which option or which value you compare. Okay. Now there's 2 more on here that I want you to read through. We don't really have time in this video to thoroughly go through them, but you've got, now this one I just did present value, and I did option 1, option 2, compared the 2, and you can easily see option 1 is definitely the higher of the 2 by 827,000. And then on this next example, I did present value, compared those. Option 2 is better. I also did future value, compared those. Option 2 is again better. But there's 2 more examples for you to go through and see if you kind of grasp this, and you will need to practice these problems. Okay. Now this last concept is actually not in this section. It's in the appendix of your book. IU has deemed this an important section, or topic, so I want to make sure we hit this as well. So there's 2 different type of percentages. You're used to the nominal rate, and that's what we've been working with all along. So if I scroll back up here, this 3.75, 4.5, 4.5, those are the nominal rate. That's what you're used to. Now they're introducing you to the effective annual yield. So the yield on an investment after 1 year, after taking into account the effects of compounding. So here's the idea. If you invest $100 in a bank account that's compounded quarterly at 7.5%, then at the end of the year, you expect your bank account to have $107.50. But that's not true. Because it's compounded quarterly, you're not just going to earn $7.50 on that $100. So if you do 100 times 1 plus 0.075 over 4, because it's quarterly, raised to the 4 times 1, and you put this in your calculator, you actually get 107.71. So you actually earned 7.71, not $7.50 like you thought. So, and that happens to be how we're able to calculate the effective annual yield, by doing 100 and then the compounded quarterly. It could be compounded continuously. But that 7.71, that's called the effective annual yield. And it's just 2 different percentages. This is your nominal rate, and this is your effective annual yield. And supposedly, banks are supposed to show you both of those percentages. So next time you're at the bank and you're opening a savings account, see if they show you both of those. Now on this last one here, let me move my face up. What nominal interest rate is needed to acquire an effective annual yield of 6.25? So we're working backwards this time. So we know the effective annual yield. So we'll do 106.25 equals 100, and we're compounded continuously. So e to the r times 1. So for this, you would divide over 100, natural log both sides, and you get 0.0606, or 6.06. That's your nominal rate. And you'll notice these are always going to be close to each other. Your effective annual yield should be higher. So, all right, email me if you have any questions.